Figure 14.4, passing a stack template object to a function template. You may have noticed in the preceding example that in main we did basically the exact same operations twice, once for a stack of type double and once for a stack of type int. In this example, what we want to demonstrate is how to create a function template that receives as one of its parameters a class template specialization, an object of a particular class template. So here in main of this example, you can see that we are once again creating our stack of double and our stack of integers. Our stack of doubles has 5 elements and our stack of integers has the default size 10. Then we call our function template called testStack, and we give it as its arguments the double stack object, the initial value of the values that we want to start pushing onto the stack, the increment of the values that we want to start pushing onto the stack, and then a string that we can use for output purposes. In the case of the second call to test stack, we give it an integer stack. We give it an int and an int for the initial value and the increment values that we'll be using while pushing, and then we give it the word int stack as part of our output. So let's see how we implemented this test stack function. In fact, before we even do that, let's run the program just to show you that we produce the same output as we had in the preceding program. Clearly, we were able to push elements onto double stack, same 5 elements as before, couldn't push once we got to 6. We reversed or popped the values out in reverse order. Then we push on the 10 values onto the int stack, couldn't push 11, and we pop the values back out in reverse order. So clearly, whatever we did to re-implement this example is working properly and has the exact same output as the previous example. Now, if you take a look at our test stack function template, you can see once again that we start the function template with the type name T in angle brackets of the template declaration. Then we have the beginning of our function definition. It doesn't return a value, so we specify void, and of course test stack is the name of the function. The first argument in this case is a reference to a stack of some type T. Now, we want to be able to process any type of stack object that we receive here, so we give it a templatized first parameter, and if I call this function with a stack of integers, it's going to expect to replace t with int here, and int here, and it's going to expect that I give it 3 int values, or I'm sorry, a stack of integers and 2 int values, excuse me, to call the function properly. If I say I want a stack of doubles, it's going to replace t with double, double, and double here, and we're going to expect to receive a stack of doubles with 2 double values after that in the argument list. And of course we also have a string that represents the stack name as well. So then we just go and we re-implemented the same code we had in main of the preceding program. We say that we're pushing elements onto some stack and we use the stack name. We then have our loop that pushes the first value that was received as the second parameter. Then we display that value followed by a space, and then we are going to add the increment value to the original value and store that in the original variable called value. And that way we increment the value for the next push operation, and we go back to the top and do it again. And of course we continue to do this until the push function returns false, at which point we say that it's full, and we display the value that's no longer that was not able to, be pushed. Then we do our popping of the elements from whatever stack was received as an argument, and we specify the stack name, and we iterate through this loop one element at a time, popping the elements into the value variable, then displaying that variable followed by a space. And once again, by the way, notice that we are using output operators with the values in the example, so whatever type you're going to use with this function template has to have an overloaded output operator associated with it so that it can work correctly and compile the code. So here we've rewritten what was done twice in the main function of the previous program as a generic function template that can then be instantiated, if you will, or specialized by the compiler based on how we call the template. And as you saw when I ran the program, we were able to produce the exact same output. So what this does is it allows you to create code that works with class templates, and then you can have function templates that can be generated into specializations for you by the compiler just based on the instantiation of the template, the class template that you happen to be using. So if I wanted to now add to this program a stack of strings or something, I could technically use that with this example as well, and test out a stack of strings or some other data type. I could certainly easily add in a stack of long integers, for example, and have that work with our test stack function.